For this problem, on the topic of circular motion, we are told that a basin surrounding a drain has a circular conic shape opening upward. We also know the angle everywhere with the horizontal. We then set an ice cube with a given mass sliding around the cone without friction in a horizontal circle. The radius of the circle is capital R. We want to first find the speed of the ice cube as a function of R. We want to know if any of the given data is unnecessary for the solution. We want to assume that if the radius is made twice as large, if the required speed will increase, decrease, or stay constant, and if it does, then by what factor? And finally, will the time required for each revolution increase, decrease, or stay the same? And the last part of the problem is to point out if the answers to part C and D seem contradictory. So firstly, we know the forces acting on the ice cube are the Earth's gravitational force straight down and the basin's normal force upward and inward at 35 degrees with the vertical. We'll choose the x and y axes to be horizontal and vertical so that the acceleration is purely in the x direction. And then we have that the sum of all the forces in the x direction must equal to max. This is by Newton's second law. And this means that the normal force times sine theta, where theta in this case is 35 degrees, must equal to mv squared over capital R. If we apply Newton's second law in the y direction, we get the sum of all the forces in the y direction must equal to the acceleration times the mass. And again, this is n cosine of 35 degrees minus the weight, which is acting in the opposite direction, must equal to 0. There's no acceleration in the y direction. So if we divide these two expressions, we can eliminate the normal force, and so we get n sine 35 degrees divided by n cosine 35 degrees is equal to mv squared over r times m times g. So we can see from here that the tan of 35 degrees is equal to v squared over r times g. So the masses cancel as well, meaning that the speed v in terms of r is equal to the square root of r times g times the tan of 35 degrees. So we can write this as the square root of 6.86 meters per square second times r. And that's our expression for the velocity in terms of the radius r. Then for part B, we want to know if any of the data that was given is unnecessary. Well, we can see that the velocity does not depend on the mass. So even though the mass of the ice cube is given, the mass is unnecessary. For the next part of the problem, part C, we want to know if the required speed will increase, decrease, or stay constant if r is made twice as large. So our answer to part A indicates that the speed is proportional to the square root of the radius. So if we increase the radius, the required speed will increase. So increasing r gives us an increasing speed. And then for part D, we want to know if the time required for each revolution will increase, decrease in the same scenario. So the period is 2 pi r for one revolution divided by the constant speed v. And this is 2 pi r over, remember, v is the square root of r times g times the tan of 35 degrees. So this becomes 2.4 seconds over meter to the half times the square root of r. So we can see for here as well that the period is proportional to the square root of the radius. So again, like before, when the radius increases, the period will increase. Lastly, for part E, we want to know if the answers to part C and D are contradictory, and our explanation is as follows. Now, on a larger circle, so if the radius is larger, the ice cube's speed is proportional to square root of r. But the distance it travels is proportional to r. So the time interval required is proportional to r over the square root of r. And r over the square root of r is simply the square root of r.